In this video, we'll talk about reflection matrices, and we'll use it as an example of diagonalization and how it's useful. And this example will hopefully tie together a lot of the different concepts you've been learning in linear algebra. So I'm going to work with R3. Okay, so you have R3. There are 2x2 reflection matrices also, but for this example, we'll work with R3. So let's say that you have a plane in R3. So for example, the XY plane. So here's the XY plane. Well, what it means to reflect a vector about the xy plane is if you have a vector like here, let's say this vector is 1, 2, 3, reflecting about the xy plane will take your vector directly across the plane, so it would be the mirror image. So let's say this is your V, and let's say T is the transformation that reflects matrices across the plane. So then TV will be down here. Okay, let's put it in purple, say. So this will be TV. Now what do you think this vector TV is going to be? So this plane is the xy plane, z equals 0. Well, what's going to happen is the x and y coordinates will still be the same, because this 1, 2, 3 vector, right, this point is directly above 1, 2, 0 on the xy plane. And then when you reflect it, so it's going to go in the opposite direction by the same length except down. So it's going to be 1, 2, negative 3. And in general, so if T is the reflection, so T reflects vectors across the plane z equals 0, then what T is going to do to xyz, the point xyz, is it's going to take it to x comma y comma negative z. And okay, we can write down the standard matrix of T pretty easily. So the standard matrix of T is, let's call it A. It's going to be well, it's going to take 1, 0, 0 to 1, 0, 0. So it's going to be 1, 0, 0. It's going to take 0, 1, 0 to 0, 1, 0. It's going to take 0, 0, 1 to 0, 0, negative 1. Right? That's the standard matrix of T. And you can check that if you take A and multiply it by xyz, you will in fact get xy negative z. So this is a very simple matrix to work with. Now, let's think about this matrix, this transformation in terms of eigenvalues and eigenvectors. So what are some of the eigenvectors of this matrix? Well, if you think about it, there's actually two types of eigenvectors. There are the vectors on the plane. So if you take a vector on this plane, z equals 0, what's going to happen when you reflect it? Well, it's going to stay there, right? Because if you're on the plane and you reflect across the plane, since the vector is already on the plane, it's not going to move. So these vectors on the plane, z equals 0, these are eigenvectors. So eigenvectors, so vectors on the plane, z equals 0 are eigenvectors. technically with the exception of the 0 vector. Eigenvectors with eigenvalue 1, right? The vectors that don't move under the mapping have eigenvalue 1 because it's just A V equals V. Okay, but there's another type of eigenvector. What other eigenvectors are there? This is a bit hidden. It's all the vectors on the z-axis. Because what's going to happen with a vector on the z-axis? It's going to, see, those vectors on the z-axis are just going to get reflected, but they're still going to stay on the z-axis. So those vectors are eigenvectors. So these are eigenvectors with eigenvalue 1. Well, this matrix is going to take a vector on the z-axis to negative itself, negative 1 times itself. Because it's going to take 0, 0, z to 0, 0, negative z. So that's multiplying that vector by negative 1. So those are the eigenvectors with eigenvalue negative 1. So vectors on the z-axis have eigenvalue. So these are eigenvectors with eigenvalue negative 1. So we can diagonalize this matrix. So how can we diagonalize this matrix? Well, because our 0 eigenspace, our null space of this matrix is just the z equals 0 plane. No, sorry. What am I saying? No. The vectors on the plane z equals 0 are eigenvectors with eigenvalue 1, and the one eigenspace is 2-dimensional, and then you have eigenvectors with eigenvalue 1, that's a 1-dimensional space. So you have 3 independent eigenvectors. So your matrix is diagonalizable, so we can diagonalize this matrix A. Well, actually, this matrix is already diagonal, but for the purpose of doing the next example, let's just come up with P. So what could we have as P? So our P, we could make, so this is our D, it's 1, 1, negative 1, and then whatever P inverse is, P will consist of eigenvectors of the eigenvalues, right? Independent eigenvectors. So the first two, if I want my D to be 1, 1, negative 1, I'm just writing in descending order, then I want the first two columns to be independent eigenvectors with eigenvalue 1. Well, those are just vectors on the plane. So I just need to pick 2 vectors on this plane, and then those can be vectors for P, as long as the eigenvectors are independent. So how about, I don't know, how about 2, 3, 0, and 1, 1, 0? I mean, it doesn't actually matter, right? These are 2 independent eigenvectors, v1 and v2 with eigenvalue 1. And now, for the last column, I just need an eigenvector on the z-axis. So that would be something like, I don't know, 1, 1, 1. Right? That's just on the z-axis. So these are linearly independent eigenvectors. And then these are, the v3 will be on the z-axis. Oops. Oh, no, I don't want this. Okay, so that's going to be P, and then P inverse is whatever P inverse is, and then we can express A like this. Now this was particularly simple, so it turns out that when you do this, if you calculate whatever P inverse is and do PDP inverse, you will in fact just get A, which in this case turned out to be equal to D. So So yeah. So there isn't really a good reason to diagonalize when your matrix A is already diagonal. I mean, right? Because, but this is just to explain the concept. Now, when you have a plane that's not, so this is leading up to the example that I really want to do, which is what happens if, so we're done with the previous example, but what if the plane is not, on the coordinate axes, like it's not x equals 0, y equals 0, z equals 0. So what if the plane was the plane given by x plus y plus z equals 1? X plus y plus z equals 0, sorry. So this is, again, a plane toward the origin. Okay, so it's, well, this plane, we can say that it's a normal vector is 1, 1, 1, right? That's a normal vector to the plane. So 1, 1, 1 is like this, and the plane is perpendicular to that vector. So the plane we're reflecting about is something like that. That's the plane. Well, now, if we want to say what the matrix A is, so again, T is reflection across the plane. And the question is, what is the standard matrix A? Well, to find the standard matrix A, normally what we do is we see where 1, 0, 0, 0, 1, 0, and 0, 0, 1 go. But in this case, it's not easy because the plane that we're reflecting about is weird. So here's where diagonalization can be useful, the eigenvectors and eigenvalues, because we can actually say what the eigenvectors are. Again, the eigenvectors with eigenvalue 1 are the vectors on the plane. So again, we can diagonalize A, because now our diagonal matrix D is again going to be 1, 1, negative 1, but now our P, okay, we have lots of different options for P, but okay, if our diagonal matrix, we chose the numbers in descending order, so they're going to be 1, 1, negative 1, then again we need V1 and V2 to be eigenvectors with eigenvalue 1, so they need to be independent vectors on this plane. Now, how can we come up with two independent vectors on this plane? Well, we just need two vectors on the plane, and to find the vector on the plane, they need to satisfy x plus y plus z equals 0, right? So all you need to do to come up with two vectors on the plane is just come up with two independent vectors that satisfy x plus y plus z equals 0. So how about just 1, 1, negative 2, 1, negative 1, 0? Do we agree that x plus y plus z equals 0? 1 plus 1 minus 2 is 0. 1 minus 1 plus 0 is 0. So these vectors are on the plane, x plus y plus z equals 0. And we can see that they are independent because they're not parallel. Right? They're not scalar multiples of each other. All right, so now we just need an eigenvector with eigenvalue negative 1. And again, those are going to be the vectors on this line that's orthogonal to the plane. It's the line along the normal vector. Well, why not just take the normal vector? I mean, we can take any non-zero scalar multiple, but let's just take n to be, or v3 to be n, right? Our normal vector, 1, 1, 1. So that's p, okay? Now we need to, so A is PDP inverse. Now we need to find P inverse if we want to say what it is. Now I'm not going to do the steps, but if you want more practice with calculating inverses of matrices, then you can go ahead and do that. And for the inverse, you're going to have a bunch of fractions. So one tip, by the way, is if you're working with matrices with fractions, don't simplify. You get stuff with a common denominator. Just keep the denominators the same. And that will make multiplying a lot easier. So I'm just going to write P inverse as 1, 6, 3, 6, 2, 6, 1, 6, negative 3, 6, 2, 6, negative 2, 6, 0, 2, 6. Okay. So that makes it easier when you're doing the calculations, if you're doing it by hand, to leave it kind of in not reduced form. And now you can just multiply these together, and you get what A is. And okay, oh dear. Well, I didn't actually say what these things are. So okay, I didn't calculate this in advance. So, but we can do PD. PD is not that bad. PD is just, the first column is just 1, 1, negative 2. Second column is just 1, negative 1, 0. Third column is negative 1, 1, 1. Negative 1, negative 1, negative 1. Now we need to multiply. Okay, I'm just going to factor out the 1/6 and then do this. And, oh.
You know your time is about up, so we got to
Okay, thank you.
Thank you.
Okay, well, I don't have time to do this because I have to leave. But you get some matrix, and that's our matrix A. And that's going to be the reflection matrix. And so you see that this makes things a bit easier once you know the diagonalization.